Alrighty, good morning, lads and ladies. Welcome back. Sorry for the slightly late start this morning. I have received no less than 55 emails over the last few days, and I'm doing my best to wade through some of those, at least the ones that are relevant before we get in here. If you have sent me an email over the last few days and I haven't replied to you, I apologize. Things have just been very, very busy. I will be clearing out my inbox today. So I know specifically a number of you have emailed me saying you want to take the test at the testing center, and I'll be getting all those reservations made for you guys today. If there are any issues, I will let you know, but I'm not anticipating them. They're usually very, very helpful over there. Of course, we are getting close to our exam. I'm going to go ahead and turn on the screen share here. We can start doing the thing. We have one more bit of new material to cover, and that has to do with inverse functions. So I do want to make sure we spend an appropriate amount of energy on that today. This is MAC1140, section number is 008, that is pre-calculus. And today is the 21st. Today we're talking about section 2.8, which is on inverse functions. Of course, I'd be doing a bad job here if I didn't remind you that our test is coming up, right? Our test is this Thursday. In case you didn't see the announcement or remember from last time. Exam 1 is during class time this Thursday, which is our next class meeting. Before we get into the material, there are one or two things I want to show you. Of course, in WebAssign, you have some homeworks and a quiz to be working on. Okay, here we are. So you have homework 7 and quiz 2. And today I'll be opening up your next homework, which is the homework for 2.8, the next section, the section we're going to discuss today. And working those things is the intended way for you to prepare for the exam, right? The idea is if you do the homework, you work the quizzes, you pay attention to what you're having a hard time with, and you get a little extra help on that, then you'll be in good shape for the test. However, if you're like me and so many other people, and kind of no matter what you do, you always feel like you need to work more, I have provided in the modules section here the textbooks review from chapter 2. I know that the ebook and WebAssign is like not the nicest to work with. So I just went ahead and took my physical textbook and scanned those pages for you. So you can work these problems as you see fit. Of course, this is not for a grade. This is not something you have to do. It's just something for those who want it. If you want to practice a little bit more, these are some of the most relevant problems. Of course, our test is going to cover chapter 1 material as well, but that is all intended to be review. So if any of the chapter 1 material is giving you a hard time, I can try to provide you with extra study material for that. But this is the textbooks review for chapter 2, which is definitely the bulk of the test. So feel free to play with these problems. If you're stuck on any of them, you can bring them by office hours. We can talk about them in Canvas messages or on Discord. Happy to do any of those things. But without further ado,
is our test going to be through the Cengage homework thing?
Functions. A little warm in here, so I'm going to turn on the fan. So the big idea behind an inverse function, there's a couple ways you can kind of try to understand this. The question that we're trying to answer, given a function f, can we find another function? And I want to emphasize that this thing should be a function. Can we find another function which exactly undoes whatever f does. So you know some examples of functions that are kind of easy to play this game with. If f is the function that takes its input and adds 3, right? F of x equals x plus 3. Then the function which exactly undoes that would be the function that subtracts 3. Or if f is the function that takes its input and multiplies by 7, then the function which exactly undoes that would be the function that divides by 7. But can we come up with a sort of general notion of this undoing function? And then can we come up with a procedure that finds it for us? And then finally, once we've got all of that, can we try to understand them in a little bit more abstract context? There are a few ways to conceive of these things, which are called inverses. One of them is using machine diagrams. So I'd like to discuss that for a second. The other and slightly more useful one is using mapping diagrams. Okay, yeah. If you want to talk, you have to hold down the space bar or unmute yourself. The easiest way to do this is just hold down the space bar. Think of it like a walkie-talkie. But I did get your message there, Megan. No, the exam is in Canvas. I think we did this last time. I can show you what the exams look like. Differential equations test, so you won't see too much of what it's going to look like. Exam is in Canvas. There's going to be 4 true-false questions, 4 multiple-choice questions, and 6-ish free-response questions. So the exam will be in Canvas. It'll look a lot like this. There'll be 4 true-false questions, each one worth 4 points. 4 multiple-choice questions, each one worth 6 points. And those, they're either right or they're wrong. And then there will be 6 free-response questions, each one worth 10 points. For the free response questions, you must type your final answer and just your final answer in the box, and then you will write out your full solution on your scratch paper, which after you complete the test, you will scan and submit to the Canvas assignment titled Exam 1 Written Work.
And it's just the free response.
The answer you type in the box must match the work on your paper, obviously. The answer is only worth 2 points, though. The remainder of the points for each free response question comes from the written work. There's going to be a lot of partial credit there. But that's the breakdown. So 14 questions altogether, a little bit of true false, a little bit of multiple choice, and the remainder free response. Free response, you got to type your answer in the box. If you don't type an answer in the box, even if you've got written work, I got to give you a 0. And if you type an answer in the box but don't provide written work, the most I can give you is 2. So just remember, write out your solutions for the free response questions, type your final answer in the box, and then move on. All right, don't wait till the end of the test to come back and type in the answers. That's not a smart move. Okay. If you want to see those details, right, check out the video from last Wednesday. I think we went through all of this. I showed you guys the sample test and everything then, right? HonorLock is an extension for Google Chrome. So you have to download the Google Chrome browser if you're not using that, and then just search HonorLock extension on Google. I'm in Firefox here, so I don't really like Chrome, but if you search HonorLock extension, you'll find it right here. And you just download it and add it to Chrome. Remember the proctoring system, again, we talked about this last week, the proctoring system, you can either take the test in the testing center and do their thing, which is fine. Just make sure you scan your work before you leave. They can have them scan your work, you can scan it yourself, you got to scan the work and submit it in Canvas. Or you can take the test online with me. If you're going to take the test online with me, you're going to have to use HonorLock, and you're also going to have to sign into Zoom on your phone. On your phone, you're going to set up somewhere off to the side where I can see your hands, your desk, your lap, and the paper you're writing on. All right, so let's answer this question. Given a function f, can we find another function which exactly undoes whatever it is that f does? So if f adds 3, this inverse should subtract 3. If f multiplies by 7, this inverse should divide by 7. And we know many functions are more complicated than that. The answer to this is yes, under some Yes, but with some asterisks, with some caveats. So to think about this in terms of the machine diagram, remember we said we can think of the function f as being like a machine on an assembly line. X's come in, and f of x's go out. In this setting, the inverse would be running the machine backwards. Right, so your inputs come in here, f does something to them and spits out the outputs. If f is the constant function f of x equals 2, then for every number that comes in, it spits out the number 2. If f is the function f of x equals x plus 3, then for every number that comes in, that number plus 3 goes out. One of the analogies that I like here when we think about this question is to pretend that f is like a machine at a recycling factory, right? They receive aluminum cans and they want to process that aluminum and get it ready to be used in other things. So maybe this machine takes in a soda can that's got like Coke or Pepsi and all the paint on it and just burns off that paint. So labeled cans come in, totally blank cans come out. The question, can we find a way to undo this, actually depends a lot on the way the machine F behaves. In that specific example where a Sprite or Pepsi or whatever Coke can comes in here, and a totally blank shiny aluminum can comes out here, if you look at all of those outputs, what would it mean to run that machine backwards? It would mean you take in each can, blank can over here, and repaint it with the logo it originally had, and send out the can with the logo. But if I've got nothing but a pile of blank silver cans over here, I don't know which logo to paint on each can. So that would be an example of a machine that would kind of be hard to run backwards because the machine destroys information about the inputs, right? The machine doesn't preserve it, doesn't have any way to tell you which blank can had a Coke logo or a Pepsi logo or something like that on it. In terms of mapping diagrams, we can make it even more clear. We have to remember what a mapping diagram is. So remember a mapping diagram, we had a set over here, which was our domain, and we had some inputs. I'll just draw 3 of them over here. And each one of those inputs gets mapped to some output. So maybe over here, these are the numbers 1, 2, 3. Maybe over here, these are the numbers 9, 13, and 7. And maybe F sends 1 over here to 9. Maybe F sends 2 over here to 13. And F sends 3 over here to 7. So the black arrows would represent the function F. The domain is just the set 1, 2, 3. That's all the inputs. And the range is just the set 9, 13, 7. Those are all the outputs. In this setting, in the setting of the mapping diagram, the inverse function would take 9 and send it back home to 1. Would take 13 and send it back over to 2. And would take 7 and send it back over to 3. So the purple here would be F. The notation we use is a little -1 looking like a power there. So the function f in black here is one where we can undo it quite easily. You just send all the arrows back the other way. You send each output for the original back to the input from which it came. And the challenge with the paint can or the soda can thing is each output, I don't know what logo that can had on it before. I don't know what input each of those came from because the outputs are all the same. Whether you started as a Coke can or a Pepsi can or a Sprite can or a Mountain Dew can, the output from the soda machine logo burning thing is just a blank can. Every input, regardless of its logo, gets sent to the same output. What would that look like in the mapping diagram? Well, before I do that, let me illustrate some of the notation here. So the original function f of 1 is equal to 9 because f, the black, sends this input 1 to this output 9. F of 2 is 13 and f of 3 is 7. And we can think about these similar statements for the purple function. The purple function sees 9 as an input, and it sends that 9 back to 1. So we would say f inverse of 9 is equal to 1. And you see the relation between these, right? The corresponding statement for the ordered pair 2 and 13, the purple function sends this 13 back to 2. So f inverse of 13 is equal to 2. And then finally, the 3, 7, f sends 3 to 7, so f inverse has to send 7 back to 3. Now, don't be confused with the -1 notation here. This is not a power. This is just the notation that's used for an inverse function. And I suppose at this point, we need to define what an inverse function is to actually move on. I see there's something in the chat there. Let's see if testing center has a room number. It does. It's in building N. I don't remember the room number off the top of my head. The question was, does the testing center have a room number? And it does. I remember it's on the second floor of building N. If you go in the main doors there, N216 is the room number there. All right. So in this mapping diagram, the black arrows do define a function. Every input is being sent to only one output, right? There is no input that gets sent to 2 different outputs. The purple also defines a function. The purple sees these things as inputs and sends each of them to one and only one output. There is none of these that are getting sent to 2 different guys on the other side. If you think about the soda can machine, though, or any function that sends multiple inputs to the same output. So again, I'll just call these inputs 1, 2, and 3. And over here, maybe we just send everything to one output, call it 5. So the original function f sends 1 to 5, sends 2 to 5, and also sends 3 to 5. In other words, f of 1, f of 2, and f of 3 are all equal to 5. So the question becomes, what is f inverse of 5? So if I turn all these arrows around, what does that new mapping thing look like? Well, it would send this 5 back to 1. It would send that same 5 back to 2, and that same 5 back to 3. So what would this be? Anybody? Yeah, so Yanni's given a good answer in the chat there, saying 1, 2, and 3, all of them, right? That's the natural thing to say. This is asking what original inputs got sent to 5. Could it be 1, 2, and 3? But remember, we want F inverse to be a function. Is it possible for a function to send the single input 5 to the 3 different outputs 1, 2, and 3? Yeah, this wouldn't be a function. So the relation F inverse diagrammed in purple above is not a function because it sends the input 5 to multiple outputs. All right, 1, 2, and 3. So given any function, you can always come up with an inverse relation, right? You can always send all the outputs back to the inputs from which they came. I can always answer who got sent to 5. But that inverse relation may not be a function, right? If I ask what is the inverse function for F, the answer is there isn't one. There isn't one because the inverse relation defined in the obvious way violates the definition of a function. So one of the things we'd like to do is say, what traits does the original function F need to have in order for that inverse mapping to also be a function? In other words, can we compare this mapping diagram to the previous one and see why the previous one had an inverse function and this one doesn't?
For each input, they have their own output.
The language you may have heard before, you may not. I don't mind introducing it. This function, the black function F, here in mapping diagram 2, is called a 3-to-1 function. It takes 3 different inputs and sends all of them to 1 output. So you've got 3 things being mapped by the black to 1 thing, 3-to-1. The black function diagrammed here is what's called a 1-to-1 function, because for every 1 input, there is 1 and only 1 output. There are no 2 inputs going to the same output, or no 3 inputs going to the same output. Every 1 input has his own output. So if you ask me who got sent to 9, the answer is the single guy 1. Who got sent to 13? The answer is the single guy 2. We don't have any of this piling up behavior like we do here. And the soda machine has the same problem, right? He takes the many different types of cans, Coke, Pepsi, whatever, and sends them all to a blank silver can. And that's why it's so hard to run that machine backwards, because it destroys the information. Who did this who did this output come from? All right. So, definition. A function F is called 1-to-1, which I will abbreviate as 1-1 because it takes a lot of space to write that, if it sends different inputs to different outputs. That's the way your book says it. Another way to say it is every input has a unique output. Every input goes to his own output. In algebra, this means if x is different from y, then f of x will be different from f of y. So I'm thinking of x and y as being two inputs. If I have two different inputs, then their outputs will be different. In other words, no two distinct inputs get mapped to the same output. And you see how this violates that, right? If I take x to be 1 and y to be 2, then 1 is different from 2, so x is different from y. But f of 1 is 5, f of 2 is 5. So we don't have f of 1 is different from f of 2. That's in violation of this definition. Yeah, I like the way you said that, Chris. There wouldn't be a result. It's not the case that there isn't an inverse mapping. There is, or there isn't an inverse relation. There is an inverse relation. It's just that it's not a function. And we want to focus our attention on functions. I have one more definition and then a theorem, and then we're going to see how to play with these things. So we've talked about this concept of an inverse, but we haven't defined it properly yet. So we can even roll these together. Given a 1-to-1 function, f, its inverse, denoted f with a -1 up here, which again is not a power, it's just the notation we use for an inverse, is the function which sends each output from f back to the input from which it came. And this can be described in algebra also. Genesis asked an interesting question. So would the inverse rule work if the input has multiple outputs? Well, if you have a relation where one input goes to multiple outputs, that's automatically not a function. So the only things that we're trying to find inverses for are functions. So that isn't a situation that we'll ever find ourselves in, where you're trying to find an inverse where the original relation sends one input to multiple outputs, because that original relation then would not be a function. How would it be if the right side have more numbers than the left side? Well, again, we got to think of the definition of a function. So a function sends every input to one output, right? Each input needs to go to one output. So when I think of this right side, I'm thinking of this as all the outputs. This is the range. So the range is by definition all the stuff that gets hit, all the stuff that is an output. The idea that your question is getting at, Chris, is the difference between something called a range and a codomain. It's possible to have elements in a codomain that don't get hit by the function. But since we're thinking of this side as being the range, by definition, everything there gets some black arrow pointed to it. All right. This latter thing can be described in algebra also. It looks the way you suspect it looks based on the stuff like this we did on the previous page. It's defined by the rule that f of some input is equal to this output if and only if f inverse of that output is equal to the input from which it came. So like if f is a 1-to-1 function and f of 1 is 7, then f inverse of 7 is 1. Now there is another way to say this. And this is the definition that most people receive when they first see this stuff. It's that if you compose, this is why we talk about combining functions before we do this. If you compose f with its inverse, meaning you take f inverse of f of x, what should this be? So x is an input,
inverse?
f of x, that's this output y, and then I'm going to take f inverse of that. What should that be?
F inverse of y.
I start with x, I multiply by 7, and then I divide by 7. What should I get out?
Just x?
Don't be shy. How about another example? How about f is the function that puts on your socks? So x is my bare foot, f puts on my socks. F inverse would then take off my socks. So f inverse of f of x, let's start with foot, put on socks, take off socks. I should get the bare foot back, right? F inverse of f of x should always be
Equal to 0.
x. Remember, f inverse is the function that exactly undoes the function f. So if you do both of them in a row to some input, you should get that input back. And in fact, it's true in the other way also. F of f inverse of x, which is this. If you want to write it out, this should also always simplify to x. And these are how you check. This is how you check or verify that two functions are inverses. So if on the test I give you two functions and I say verify that these are inverses of each other, you need to compute both of these and show that both of them simplify to x. Okay. The big question we're going to have to deal with here is how do you find the inverse? If I give you the function f, how do you find the inverse function f inverse? And I'm going to show you how to do that, but first I want to just give you a little bit of practice with this. For example, show that f of x equals, I don't know, 2x minus 3, and f inverse, this should be 2 are inverses. What we need to do we need to show that f inverse of f of x simplifies to x, and f of f inverse of x simplifies to x. Right? That's what we said. That's how you check or verify or show that two functions are inverses. You compose them in both directions and verify that you always just get x. Let's do this one first. F inverse of f of x. That's by definition f inverse of f of x, like this. f inverse of 2x plus or 2x minus 3. Remember, when you do these compositions, you work from the inside out. I know what f of x is, it's 2x minus 3, and I want to take f inverse of that. So I'm going to plug 2x minus 3 in here in parentheses for x. That's 2x minus 3 plus 3 all over 2, which is 2x over 2, which is indeed just x. So things are looking good, but we still need to check the other direction also. It is possible for one of these to simplify to x and the other one to not simplify to x. Those are called left inverses or right inverses. You won't run into them in this class, but they do exist. So I'm obligated to tell you you need to check both ways. This will be f of f inverse of x. The inner thing there is x plus 3 over 2. And if I'm going to take f of that, that means I take this formula for f of x, and here, in place of this x, I write x plus 3 over 2, all in parentheses. So that's 2 times parentheses x plus 3 over 2 minus 3. And the 2's cancel, and you get x plus 3 minus 3, which is also x. So yes, these are inverses. So our long-term goal here is to be able to compute the inverse of a function, right? If I give you this thing, can you find this thing? And it's not terribly hard. I think you can probably see the relations between this and this. You can do it verbally quite easily, especially if the function is very simple. So here, the original function, what does it do? It takes its input, x, multiplies by 2, and then subtracts 3 from the result. So if we want to undo that, we need to undo each of those steps. And we have to do it in reverse order. So to undo the operation multiply by 2, then subtract 3, you would add 3, and then divide by 2. Just like when you put on your socks and shoes, to undo that, you take off your shoes, then take off your socks. You can't take your socks off first. So if you have a verbal description of the original function, you can come up with a verbal description of the inverse function by reversing each step and reversing the order of the steps. So if the original function were to cube the input and then add 5, the inverse function would have to subtract 5, then take the cube root. And I'll give you a procedure for finding inverses in just a second, but before we do that, remember the only functions that have inverses are one-to-one functions. So we need to know how to tell if a function is one-to-one. Well, if you have the mapping diagram for that function, it's easy, right? You just look and see, are there any two arrows that point to the same output? If you have a table for that function, it's very easy. Again, you just have to ask yourself, do different inputs go to different outputs? Do any outputs get repeated? But we often don't have either of those things, right? Most of the time, we just have some algebraic representation of the function like this, or maybe a graph. And you know how to get graphs of nice, simple functions. So the big thing here is going to be to figure this out using the graph. This is called the horizontal line test. And what it says is if any horizontal line hits the graph of the function f more than once, then f is not one-to-one. Start using that abbreviation. And I'll try to explain why this is true. But it's kind of like a backwards version of the vertical line test. Remember, the vertical line test is a way to tell if a graph is a function. If any vertical line hits your graph more than once, then automatically that is not the graph of a function. The horizontal line test says if any horizontal line hits your graph more than once, then that's not a one-to-one function. The reason for this, picture here to think about. I have some graph here, and I imagine drawing in a horizontal line, and I see, oh shit, that horizontal line hits my graph in two places. That means that this point and this point are made up of x values and y values. I'll call this maybe x1 and x2, both of which go to the same y value. So since the points lie on the same horizontal line, f of x1 is equal to f of x2. In other words, f sends both x1 and x2 to the same output, i.e., or hence, f is not one-to-one. Right, whatever that y value is, that's the output for x1, and it's also the output for x2. So both x1 and x2 are sent to that same output, which means this is not a one-to-one function, right? One-to-one functions are functions that send every input to a different output. No two inputs getting sent to the same output. So this is in direct violation. I don't think you guys are going to need much practice with this. You just imagine drawing horizontal lines. If any horizontal line touches that graph more than once, then automatically that is not a one-to-one function and hence does not have an inverse. There are ways to kind of throw away half the graph. Like maybe I toss this part away and I just hold on to the part over here. That on its own would be one-to-one, and we could find an inverse for it. But we're going to postpone that discussion for now. Just focus on functions which are one-to-one. Okay. How do you find an inverse? So if I give you the function f, give you the algebraic representation of the function f, like a formula for f of x, how do you find f inverse? Well, here's a procedure. I've got 5 steps for you. And this might be a little bit different than what you learned in high school or elsewhere, so I want you to pay careful attention. First, let me see first, write y for f of x. All right, so you've got like f of x equals 2x minus 7. You're going to rewrite that as y equals 2x minus 7. Then and this is where things are maybe different than what you heard in the past, you're going to solve for x. And there's a reason I'm having you do it this way. Then you're going to check any domain restrictions. If the original was not one-to-one. Why I'm afraid to use that abbreviation. I'm just worried that you guys won't recognize what I'm saying. So this third step here is a special step for trying to invert functions that are not one-to-one. There is a way to do it. You have to restrict the domain of the original function. For what we're going to do right now, this is not relevant, but I will show you examples where the original is not one-to-one, but you're still able to find an inverse. The trick is that you have to restrict the domain of the original to make it one-to-one. And sometimes that introduces some weirdness in the algebra when you solve for x. So after you've solved for x, you're going to need to take a look at that algebra and see if your domain restriction tells you anything. Like maybe you have a plus or a minus that shows up somewhere that needs to be flipped, or you need to choose between a plus minus when you've got both. Then you're going to swap x and y. And then finally, now y is f inverse of x. So you can rewrite y as f inverse. This is how you find an inverse function. I'm going to do it for you first for a function that is one-to-one. And then I'm going to do it for a function that's not one-to-one. And you'll see why that step 3 is important. You'll also see why I'm telling you to wait to swap x and y. This is the big difference. Most people start by writing y for f of x, then they swap x and y and solve for y. This is a bad way to do things because you can run into trouble with these domain restrictions. So trust me, this is how I want you to do things, and it will help you. It will avoid running into mistakes if you do it this way. So please, please. All right, let's do it.
Can I ask a question?
Let's find f inverse of x, where f of x, the original function, is x over x minus 2. Now your first thought would be, is this function one-to-one? You might not know what the graph of this looks like. Let me just show you in Desmos really quick. Oh, are you having problems hearing me?
No, some people are like asking questions, but I don't think you can hear them.
I'm sorry, Ashley, can you repeat that?
Some people are asking questions, but I don't think you can hear them.
Oh, I see, I see. All right, I can hear you fine. Could you just repeat the questions, please, people? I'm sorry.
Can you hear me?
Yes, Megan, I can hear you.
Okay. I know that you said that we don't have to worry about that right now, but you just said that only one-to-one functions have inverses.
That's true, yeah.
How would number 3 play into that? Or am I getting like ahead of myself?
So the idea is that many functions on their natural domain are not one-to-one, like x squared, right? X squared is not one-to-one. It fails the horizontal line test. But if I throw away half of that parabola, so you just have this half on its own passes the horizontal line test. So while I can't invert the whole thing, I can invert just this half.
Oh, okay, I see.
That's the idea. And we think of that as a different function. That new function with the restricted domain is one-to-one. But I know that's a little bit complicated, so I just wanted to do a simpler example first.
Okay.
So before we begin running this procedure, I'd like to check if this function is one-to-one. To do that, I'm going to look at the graph in Desmos. And we will imagine here f of x equals x over x minus 2. Here's that graph. And we want to ask, does this pass the horizontal line test? Definitely up here, it looks like it does. Down here, it looks like it does. We might get a little worried in here. So just for fun, plus on the slider, delete the x. All right, here's the horizontal line y equals a for a bunch of different values, and I can move it around. And where we're worried, it looks like maybe the blue line will hit the red graph more than once, but it doesn't. So as we bring it up here, it's just hitting this part of the graph. And as soon as I get above 1, it's going to switch to the other part of the graph. And this line, y equals 1, actually never gets hit because that's a horizontal asymptote for this guy. And then he transitions up here. So this blue line never hits the graph more than once. So this really is a one-to-one function. So we can go ahead and run this procedure to find its inverse without worrying about any domain restrictions. All right. First, we write y for f of x. Next, I want to solve for x. Can anybody suggest how to get started solving this expression for the variable x? I want x equals some stuff with no x's in it.
Make it be equal to 0.
Well, I don't want to plug anything in for y or for x. I just want to take this thing and rearrange it so x is equal to some stuff involving y. It's okay if it doesn't jump out at you right away. I'll tell you, my pre-calculus teacher gave me this problem without having shown us anything like this on a test. And I remember almost crying during that test because I stared at this, I knew what to do, but I just didn't know how to do it, and it drove me nuts.
Would you multiply it by x minus 2 over x minus 2?
Perfect. Yes, exactly. We're going to cross multiply by this x minus 2. So on the left-hand side, I'll have y times parentheses x minus 2. And on the right-hand side, the x minus 2's would cancel, and I just have x. So now we're getting closer. I've got this x over here, but I also have an x over here. And I want to get just one x equals some stuff with no x's. So any ideas what we could do next?
Would you subtract the x from the left and add it to the right?
That's very close. So before I do that, your first step there, subtracting this x over is great. Before I do that, let me distribute this y. So then I'd have y times x minus 2y equals x. Here's the thing to keep in mind, right? Here's the trick. You want to get all the terms that have an x on one side and all the terms that don't have an x on the other side. Once you do that, you'll be able to factor an x out on the left and divide over by whatever remains. So this 2y, I'm going to bring him over here. And this x, I'm going to bring him, like you said, over here. So the y times x, I leave that on the left because it does have an x. This x I subtract over. And this minus 2y, I add him over. Now, since every term on the left-hand side has an x, I can factor an x out. And what's left would be y minus 1. And the 2y is still chilling on the right-hand side. Now, if I divide by y minus 1, I'll have x equals 2y divided by y minus 1. We have solved that for x. Done. So that's step 2. Step 3 here, I'm going to continue over here, conserve some paper. Step 3, the original f is 1-to-1, so there's no domain restriction. To worry about. Which means we can move to step 4, which is swapping x and y. So I take this expression right here, and just where there's an x, I write y. Where there's a y, I write x's. So that's going to be y equals 2x over x minus 1. And now finally, this y is f inverse. So f inverse of x is 2x divided by x minus 1. And that is your inverse function. You are done. this one came from factoring an x out from this expression. So look at these two pieces right here. The question is, where did the 1 come from? If I take this and I factor out an x, this piece is y times x, so he becomes a y. This piece is 1 times x, so he becomes a 1, and the minus is the minus. So I'm factoring an x out from this, and that gives me this x times y minus 1. That's where the 1 came from. If you want to check, just redistribute this x. Ask yourself, if I redistribute this x, would I get this? X times y, yeah, that's yx. And x times 1, yeah, that's x. So without this 1, when you redistribute, you wouldn't get this minus x, which we know we should have. Now we could take the time to compose this with this to verify that they are inverses. We've already done one of those, so I don't want to burn the class time on it. But if you wanted to check your work, that's how you would do it. You would plug this into this and verify that that simplifies to x. And then plug this into this and verify that that also simplifies to x. Okay. Any other questions on this this example here where we found the inverse function?
I have a question, but it's not about this problem. So for part 3, where it says like to check any domain restrictions if it's not 1-to-1, are we gonna go over a question that like has that too?
Yep, that's next.
Okay, perfect. Thank you.
Let's go ahead and do it. If there aren't any other questions on this, let's go ahead and do that. Okay. So I want to find the inverse to f of x equals x plus 3 squared. I can graph this. I know how to graph this. Let's check if this is 1-to-1. How do I get the graph of f here? What's the parent function and what do I need to do to it in order to get this graph?
Would the parent function just be like a regular parabola?
When you say regular parabola, what do you mean? Yes, but let's be more specific.
Starting at the origin, like 1 point at the origin, 1 point at like 1, 1? No, that's wrong.
No, that's correct.
It's a regular parabola, but you put it 3 to the left.
Yeah, it's x squared, right? The parent function here is x squared, which has its vertex at the origin and looks like this. It does go through 1, 1 and negative 1, 1. And then Pierre's correct. We would need to translate 3 units to the left. Shift 1, 2, 3 to the left. So here is the graph of f of x. And clearly this fails the horizontal line test, right? Like big time. If I draw a horizontal line anywhere over here, it's going to hit the graph multiple times. This is a 2-to-1 function. However, so this is not 1-to-1 on its natural domain. When I say natural domain, I just mean domain, right? The domain of this function is all real numbers. If I don't do anything to the domain, then this is not a 1-to-1 function. However, if I restrict the domain to the interval -3, comma, infinity. That means I'm just holding on to the part of the graph above the blue shaded region here. So I'm restricting to this domain. Then that is just this part of the function, which is 1-to-1. So I'm like throwing all of this away. If I restrict the domain to -3 to infinity, the function becomes 1-to-1. This is going to be a very big deal in your trigonometry class. All of your trig functions, anybody taking trig right now knows this, all of your trig functions fail the horizontal line test, right? Cosine, sine, tangent, they are all periodic. So they're all actually infinity to 1 functions. Very, very nasty. So when you want to invert those, and you will, you'll need to restrict their domains. Same is true for any quadratic function. All quadratic functions fail to be 1-to-1. They're all 2-to-1. Many other polynomials, many other functions in general, which are not 1-to-1 on their sort of natural domain, can become 1-to-1 if you restrict their domain sufficiently. I could have restricted from -2 to infinity, but I want to get as much as I can. So I want to take either this whole half or this whole half. So chopping at the vertex is what makes sense for a parabola. Now I can restrict this new I can invert this new function. This new restricted version of f of x equals x plus 3 squared. We can invert it. We just have to remember that the only x values which are allowed are those which are bigger than or equal to -3. Let's run through that procedure, and I'll show you where that step 3 becomes so important. So first, no, none of the other steps change. First, we write y in place of f of x. So y equals x plus 3 squared. Next, I want to start solving for x. What's the first step in solving an equation like this for x?
Should you go ahead and square everything?
Well, so everything on the right-hand side is already squared. I want to get rid of that square. So how do I get rid of a square?
Take a square root.
Yeah. And remember, when you take square roots in an equation, you get a plus and minus. So when I take the square root here, I'll get plus minus square root of y is equal to x plus 3. And it's that plus and minus that's going to give us a little bit of a headache unless we remember step 3. From here, I can subtract 3 from both sides. So I get plus minus square root of y minus 3 is equal to x. And that's it. Now you've got x on its own, right? Now here comes the fun one. We restricted our x values to the interval -3 to infinity, right? The domain is the x values, and we restricted the domain to this interval, -3 to infinity. You need to choose the plus or the minus. That's the thing, right? If you have both the plus and the minus, then this couldn't possibly be a function because it would be outputting 2 different values for each input. The reason we delay swapping the x and the y is so you can match these values up with this domain restriction. You see here, I have x equals plus or minus root y minus 3. And I need to know, do I take the plus or do I take the minus? If I take the minus, so let me say this. So we need to choose between the plus or minus in the plus minus square root y minus 3 equals x. If you chose the minus, then you would have negative square root of y minus 3 equals x. Those are both negative, right? Negative square root of y is always going to throw out a negative number. And if you subtract 3 from a negative number, you're going to get more negative numbers. Another way to think of this is as negative 3 minus the square root of y. So that means your x values would be starting at negative 3 and then getting more negative. On the other hand, if you take the plus, then you have the positive square root of y minus 3 equals x. That means that your x values would be starting at 0, right? Positive square root of y. And then you subtract 3 from that. So you would be taking this set of x values translated to the left by 3. Oh, that is my domain. That's the domain I chose to restrict to. So you have to ask what choice of the plus or minus gives you the correct x values. If I go with the minus, then this, which is equal to x, will always be negative. Will always be to the left of negative 3, which is this subset of x values. If you take the plus, then your x values will be from negative 3 to infinity. Oh, and that's precisely what we chose to restrict to here. So, based on our choice, based on our domain restriction, which we chose, we need to take the plus. So here, so for us, x is equal to the positive square root of y minus 3. Right? So this is a step where there really is a bit of thinking involved. You have to make a decision at the start. When you choose to restrict your domain, I could have chosen either one of these, this set or this set. I could have chose to keep the left half of the parabola, but I chose to keep the right half. We could have chosen either. The way I guide this, I always choose the domain restriction that lets me include 0. I like to have 0 in my domain. So that means we have to choose the plus or minus here that will allow me to get x equals 0 out of this. Right? If I go with the minus, then there is no y value that will let me get 0 out of this. If I go with the plus, then y equals 9 lets me get 0 out of this. So we know we have to go with the plus. There are lots of ways to think about it. Now that we have accounted for our domain restriction, we can swap x and y. So I have y equals the square root of x minus 3, and hence f inverse of x is the square root of x minus 3. And that is the inverse for this function with its domain restricted from negative 3 to infinity. Let me show you some shit in Desmos. All right, I'll give you a second to write. I want to show you some stuff in graphs. How am I doing on time? All right, here we go to Desmos. 12:13. We are out of time just about. That's okay. All right. So my original function was this guy, right? And I chose to restrict the domain. Here's how you do this in Desmos to this set. X is greater than or equal to negative 3. So I'm throwing away the left half of the parabola. The inverse function I found is this guy. And you see there's some nice symmetry here, right? The original function and the inverse function, they look very similar. In fact, that symmetry is about the line y equals x. So if you reflect the original graph over the line y equals x, you'll get the graph of the inverse. If we had gone with the other restriction, then I could have taken the other sign on the square root for my inverse. And again, you see that symmetry. So this is your procedure for finding inverses. I know we are just about out of time, but there's one more thing I need to share with you before I let you go, and it's a very important theorem. Not a stupid question. No, you cannot use Desmos during the test. But remember, these are all things, if we had a little bit more time, we can graph all of this shit by hand, right? The original function here was a shifted version of x squared. This inverse function is a shifted version of the square root. Those are both things that we can graph by hand. And there will be a problem on the test where I ask you to graph a function and its inverse, but it will be stuff that you know how to graph. All right, here comes a very important theorem. On characterizing inverses. The theorem says the following are equivalent. Meaning each one's equivalent to the other. Each one implies the other. First, the point A comma B is on the graph of the original function, f of x. That is equivalent to saying f of A is equal to B, right? This is always f of this. If I told you 1 comma 3 is on the graph, you could tell me that f of 1 is equal to 3. Then by the definition of the inverse, this is the same as saying f inverse of B is equal to A. And by definition of the graph, this means the point B comma A is on the graph of the inverse function. So this theorem is hugely important for understanding what inverses do, especially with respect to graphs. If you take items 1 and 4, AB is on the graph of F, means BA is on the graph of F inverse. That means you can take any point on the graph of F and find the corresponding point on the graph of the inverse function. Let me return to this picture. Let's go back to the one that we chose. So the point 0 comma 9 is on the graph of the original. That means that 9 comma 0 will be on the graph of the inverse. Where do I have nice points here? What's the next integer coordinate point? What's this integer coordinate? Yeah, it is. Come here. -1 comma 4 is on the graph of the original. So what point do I expect to be on the graph of the inverse?
4 comma -1.
Exactly. And right over here is 4 comma -1 on, oh, come here. I don't know why this is being so difficult. 4 comma -1 is on the graph of the inverse. The fact that there's that symmetry is exactly what it means to say that these graphs are symmetric about the line y equals x, right? The fact that A comma B being on the graph of F tells you B comma A is on the graph of F inverse. What's the difference or the relationship between those points, like 1 comma 3 and 3 comma 1, or 0 comma 9 and 9 comma 0? Those pairs of points are all symmetric over that line y equals x. 0 comma 9, 9 comma 0. Right? Each pair of points here have that symmetry. If you reflect this point over this line, straight over the line y equals x, you get this point. If you reflect this point straight over the line y equals x, you get this point. So if you have the graph of f, you can get the graph of f inverse from it. If you have the graph of f inverse, you can get the graph of f from it. And if you're graphing a function together with its inverse, you should check that you have this sort of symmetry. All right, that's really everything we need to know about inverse functions. There is a homework that I'm going to pop open for you right now, and that together with your quiz should provide you substantial practice. I do know that the test is coming up just a few days after we covered this, so the test will be gentle when it comes to inverse functions. But let me tell you one thing very clearly. This procedure, where you have to restrict the domain and then find the inverse for that restricted function, this will be on the test, right? This is something I have to make sure you guys know how to do because it's crucial for trigonometry and calculus. It's not that bad. You look at the graph, you decide which portion to keep and which portion to throw away. Identify that domain restriction, right? What is that interval that you are now considering your domain? And then as you go through your process to solve for the inverse, you'll get something like a plus or minus, right? You'll have some decision that needs to be made between the plus or minus that you're going to go with. When you go to make that decision, do I take the plus or do I take the minus? The way you choose is by thinking about your domain restriction. All right, if you do have trouble with any of this stuff, you can bring it by office hours, send me an emails, post it on the Discord, or send me a message on Canvas. I am working through the emails. I just got so many over the last couple of days that I haven't been able to get them all answered, but I will get them all answered today. And if you've requested to take the test in the testing center, I will be making those reservations this afternoon. That is it from me, guys. I got to scamper. Take care.